In this section, we're going to work on parametric equations. So we've learned how to graph equations in a different coordinate system, in polar coordinates, and seen a number of applications there. And so we kind of broke away from this familiar rectangular or Cartesian coordinate system to graph in a whole new way. In this section, we're going to definitely graph in a new way, but we are going to go back to the rectangular coordinate system to do so. But at the same time, the way we're going to produce graphs is going to be different. So when we talk about parametric equations, we're talking about a system of equations that is a pair of functions, and the two functions tell you the x value and the y value separately, right? So one function gives you the x value for a point on the curve, and the other function gives you the y value, and both of those functions are based on what we call a parameter, a value t. So what I think is really helpful to understand parametric equations is to think of t as time. So what this does is it allows us to create graphs, create curves in the xy plane, and also keep track of the time at which certain points are achieved. All right, so let's do example 1 here, and we'll kind of see how this all plays out. So we're told that we're told to sketch the graph of the curve defined by the equations x equals 2t and y is equal to t squared minus 1, where t goes between -1 and 2. Okay, now this, you're thinking of time, you might say, well, oh, does negative really make sense? Well, you can still think of time, -1 meaning like 1 minute before a particular event, and then 2 is 2 minutes after that event. So, negative time can make sense. So what we're going to do is we're going to just create a table where we first keep track of t, and then we'll keep track of x, which we're told is always twice whatever t is, and then we'll keep track of y, which is t squared minus 1. All right, and so let's just kind of do the obvious thing here, which would be to go ahead and plot all the integers, integer values of t in this interval. So we'll go -1, 0, 1, and 2, and then we'll see if that gives us a good picture of what's happening. So if t is -1, of course that means x is -2, and then it means that y is -1 squared minus 1, which is 0. So when t is equal to -1, x is -2, y is 0. So of course the parameter t is not visible on the graph, but what I know is that this point is achieved when t is -1. So again, thinking of time, we could say we're at this point, 1 minute before a particular event. All right, if I put 0 in, I of course get 0 for my x, and then -1 for my y. So 0 for x, -1 for y puts me right there. And then when t is equal to 1, we get 2 and 0. So that puts us at this point here. And then finally, for our largest t value, t equals 2, x equals 4, and y equals 3. So that puts us right here. All right, and so you can probably get a pretty good idea of what's happening here. All right. So there we go, and while you don't have to do this normally, I could just mark t equals -1 as there, right? T equals 0, t equals 1, and t equals 2. And then sometimes what we do as well is to indicate as the parameter increases, basically how is the graph drawn out, we might put little arrows along here just to indicate over here are smaller values of t, and as we go this way it's larger values of t. All right, now if I look at this graph, it should look familiar. It looks a lot like a parabola, and maybe that's not too surprising because I see a t squared right here. Right, but now to really convince ourselves that this is a portion of a parabola, what we want to do is something called eliminating the parameter. Okay, and that's the way that we convert from parametric equations into rectangular coordinates. So you basically just treat this thing like a system of equations, right? So you have x is equal to 2t, and you have y is equal to t squared minus 1. And in this system of equations, basically our whole goal is to write this without t being involved. So I have equation 1 and I have equation 2. And if I look at equation 1, it looks like it would be really easy to isolate my t. So taking equation 1, I can say x divided by 2 is t. But then what, of course, that allows me to do is in equation 2, I can place x over 2 in for where t was. And so that gives me y is equal to x squared over 4 minus 1. And so, of course, we confirm this is a parabola. It's a parabola shifted down 1, right? And I'm dividing by 4 here. And so, normally I would go over 1, up 1. But instead I'm going to go over 1 up a fourth, and that seems, somewhat accurate to the graph that I drew. So this would be those parametric equations expressed in rectangular coordinates. All right, so let's look at another example here. All right, we're going to graph these parametric equations, x equals 4 cosine t, and y equals 4 sine t for t greater than or equal to 0. And then we're going to write the equation in rectangular coordinates when we're all done. So just like on the last problem, let's make a table here. X is 4 cosine of t, and y is 4 sine of t. Okay, so we're saying t should be greater than or equal to 0, so let's go ahead and start at 0. All right, so the 4 times the cosine of 0 is 4 times 1, so that's just going to give me 4. And then I know that the sine of 0 is 0. So when t equals 0, I'm at the point 4, 0. Now I think probably what makes a lot of sense here is to go ahead and plug in special values on the circle as I go around here. So I've got a number of values to do, so I'm going to go ahead and just do pi over 4. So I'm not going to do every single one. So let's go 4 cosine pi over 4. So that is equal to root 2 over 2, so that ends up being 2 roots of 2. And then for sine, it's going to be the same thing. 4 sine of pi over 4, that's going to be also 2 roots of 2. And I should probably just go ahead and get an approximation here. So 2 roots of 2 is approximately, didn't leave myself quite enough room, 2.83. Approximately 2.83. Okay, so what that means is that I'll go over 2.83 and up 2.83, putting me, right about there, I guess. right, so that's going to be a point on my curve. So let's try pi over 2. So I'm not going to do all the detail work here, but if I plug pi over 2 in for cosine, I get 0. And when I plug pi over 2 in for sine, I get 1. So that's 4 times 1 is 4. So now I'm at 0, 4. If I plug in 3 pi over 4, better extend this down a little bit, then when I plug that into cosine, I get negative 2 root 2. Because you get negative root 2 over 2 here, cancels with the 4, negative 2 root 2, so that's about negative 2.83, just like we saw above. And then over here, the sine of 3 pi over 4 is still positive, so that's going to be 2 root 2, which is approximately 2.83. So now I go to the left 2.83 and up 2.83, puts me right about there. And then pi, we're at negative 4, 0. At 5 pi over 4, now I'm just going to jump straight to doing approximates. This is going to be negative 2.83 approximately, negative 2.83. And by now you're probably starting to guess as to what we've got going on here. Really, it seems like we're just forming a circle. 3 pi over 2 is going to be 0, negative 4. And then 7 pi over 4 is going to be 2.83, negative 2.83. So puts me in that neighborhood right about there. And so it certainly seems like we're forming a nice circle here. And I'll do my best to graph this. It's tough to do on the computer. All right, so we'll just have to use our imagination that that's a circle. All right, so is this surprising? Well, it shouldn't be, because remember that the cosine of an angle gives you the x value on the unit circle, and the sine of an angle gives you the y value on the unit circle, and multiplying by 4 should just change the radius of the circle to a radius of 4. So this is not altogether unexpected. But it does say to write this using rectangular coordinates. Now I could kind of cheat here and just say, oh, I know how to find the equation of a circle with radius 4 centered at the origin. But let's talk about how do we use the parameter values to do this. In a case like this, I don't think we're going to have very much luck trying to get t all by itself, right? Because it would involve sine inverses and cosine inverses and things like that to get t by itself. That doesn't seem very appealing. However, what I can do is this. I always have in my back pocket our favorite identity, right, which is the Pythagorean identity. So anytime I can make sine squareds and cosine squareds add together, I know that that turns into 1. So I'm gonna do that. So I'm gonna take x squared plus y squared. And the reason I'm doing that is because I recognize that if I square the 4 cosine t and I square the sine 4 sine t, the good things are going to happen. Oops, that should be a t squared. So that means x squared plus y squared is equal to, is equal to 16 cosine squared t plus 16 sine squared t. But if I factor out a 16, I don't know what button I keep hitting, I apologize. We get 16 times cosine squared t plus sine squared t. And of course I know that when I do that, cosine squared plus sine squared is always going to equal 1. So that leaves me with the equation x squared plus y squared equals 16. In this last example, I would like to not only graph these parametric equations and also eliminate the parameter to see what the rectangular equation is, but also use our graphing calculator to help us out. So you can see our graphing calculator over here on the side. I have something else showing here, so let's go ahead and quit there. All right, so first let's just go ahead and sketch this graph ourselves. So we'll make a table as we have on the previous examples. So here's my t, my x, and my y. Right, so I know that x is going to be -2 plus t and y is going to be 1 plus 2t. And it doesn't give me any particular t values to work with necessarily. So let's just kind of think ahead a little bit here. My x value is -2 plus t. So obviously if I pick something like -20 for t, that's not very useful because I'd get x equals -22 and that's nowhere here on the graph. So let's be smart about what we pick. Let's go ahead and pick -3 for t because a -3 would give me a -5 for x, and that's the furthest to the left the graph is showing. So I'd get -5 for x, and then I plug in a -3 in here. I get 1 plus -6 would give me -5 for y as well. So I'm over here at x equals -5, y equals -5, so way down here in the lower left corner of the grid. All right, so let's do some more here. -2 plus -2 is -4. Here we have 1 plus 2 times -2. That's going to give me -3. So -4 is my x, -3 is my y. That puts me there. -1, x is -3 if that's the case. Y is -1 when I plug -1 in for t. So that puts me there. And so we might be able to start recognizing a pattern forming and feel like we know what this equation looks like, or what this graph is going to look like. All right, and one more here. If t is equal to 2, then x is equal to 0, and y is equal to 5. All right, so it probably shouldn't surprise you. If you have both of the t's being raised to the first power, then it probably isn't too surprising that we end up with a line as the equation. All right. All right, so let's go ahead and eliminate the parameter here. So I have x minus x equals, -2 plus t, and I have y is equal to 1 plus 2t. So in equation 1, we can turn that into x plus 2 equals t. And so then in equation 2, we can say y is equal to 1 plus 2 times, and instead of t, x plus 2. So y is equal to 1 plus 2x plus 4, and so I have y is equal to 2x plus 5. All right. Now, of course, let's just do a quick review of what we know about lines. We know that this is the slope, right? And this is the y-intercept here, right? So I want to pay particular attention to the slope. So my slope is 2, and I can confirm that over here. I go up 2 over 1, up 2 over 1, right? So the slope is really 2 over 1, right? Gives you the rise over the run. But also, I want you to look at what's happening in the equation. In the equation, I have a 2 as the coefficient in front of the t for the y, and a 1 in front of the t for the x. Now, changing t is the thing that changes y and changes x. So if you think about it this way, suppose that I change t by a certain amount here and here, right? I changed the t values are the same. Then for however much I change t, then in the y value is going to change twice as much as the x value, which has a 1 in front of it. So the coefficients in front of the t are what form my slope. Okay? So as a completely separate problem here, if I had x equals 3 plus 5t, and I had y equals 2 minus 7t, just by looking at those two equations, I would say that this is a line with a slope of -7/5, right? Because I can see that when y changes, right, if t changes by 1 here, then y goes down 7 as x gets bigger by 5. So hence a slope of -7/5. Okay, so that's just one point I wanted to make. But the other thing is I wanted to show you how to create graphs of parametric equations in the calculator. All right, so just as we did with graphing polar equations in the calculator, we're going to have to switch modes. So I select mode, and then I'm going to go down, and the same place where I changed to polar coordinates, I'm going to select parametric. And I'm going to quit. And then if I go to the y equals menu, it's got a slot for x and for y. So I go ahead and type in -2 plus my variable button t, and then 1 plus 2t, and then I'm just going to hit zoom standard because I'm not sure what my graphing window looks like right now. Oops, I hit the wrong one there. Excuse me. I just kind of jumped the gun a little bit there. There we go. All right, so there's my line. Now, why is my line stopping where it's stopping, right? If you compare that to my graph, it certainly seems to go below the x-axis here, so why am I stopping? Well, the answer is when you go to Window, it's set to graph certain values of t, and it's going from 0 to 2 pi. I don't really want to do that, so let's go ahead and just graph t's from -20 down to 20. Okay, and if I hit graph there, now I'm going to get a much more complete picture. All right, so the last thing that I want to do is in example 4. Well, we already graphed the curve from above, or the line, I guess, and then I also want us to graph this. So essentially, I just want you to change the power on t to the 5th power. So instead of the 1st power, it's the 5th power. But notice that they're both the 5th power. So I'm going to go in the y equals menu, go down to the red graph, and I'll just type in -2 plus t raised to the 5th power. And then I'll type in 1 plus 2t raised to the 5th power. So when I graph that, bear in mind this is the red one, right? When I hit graph, it's going to take it a second. The red one just graphs right over the blue one. So in other words, changing the power here did not change the graph. So if these two, if the powers on the parameter value t are the same, that does not change the behavior of the graph. All that does is change how quickly things are happening. Okay? That changes how quickly things are happening. So for example, when t was equal to 2, I was at the point 0, 5 in the original. Okay? So that I was right there at that point. Okay? Now, when I have the fifth root, if t is equal to the fifth root of 2, okay, and the fifth root of 2 is a number that's pretty close, it's between 1 and 2. The fifth root of 2, that is when they're going to be at the point 2, 5, okay? So what that means is while the red graph and the blue graph are the same, again, let's use the analogy of time. The time at which the two graphs arrive at particular points is going to change.